Okay, so it's week 6, and sorry about the backlighting, but I guess it's not that bad. We'll finish up chapter 4 on bioenergy, so we're ready for the second exam, and then let's also just drop into the syllabus for a second and catch up to see what else is due here. Week 5 and 6, so we're done with week 5. All the way to the bottom. Okay. So problem set 1. Okay. So problem set 1 is due before exam 2, but we're gonna finish chapter 4 today. I'd like you to have problem set 1 done a week from today. So get in there. That's what you should focus on. Like I said, we're gonna finish up chapter 4 today, so that you can get into exam 2, and that will be due 2 weeks from today. So problem set 1 is will be late if you're turning it in more than 1 week from today, and exam 2 will be overdue if you're finishing it more than 2 weeks from today. So problem set 1 is officially due 2 days from now on Thursday, and it's officially late a week from today. Yeah. Okay. So let's get into chapter 4. Do you guys have any questions on problem sets at all? Units, all that? It's all good? Okay. Okay. So let's get into courses into 102. Chapter 4, and then I'll just take a really quick spin through the first two things. So we've looked at kind of the fundamentals of energy flow, photosynthesis. We've talked a little bit about CO2, how it's going into and out of the atmosphere. Talked a fair amount about the absorption spectra of leaves and why they're green. Now I don't think we got too much into these guys, so let me just let me hit this figure a little bit. I have come up with a lot of other similar figures on my own over the course of trying to deal with biomass, and it does get pretty complicated. But the majority of these technologies that we're seeing right now have been developed. Okay, so what we're looking at is figure 4.4, making use of biomaterials. So there's a wide variety of classes of biomaterials, first of all. So everything sort of here on the left is sort of biology, if you will. The stuff in the middle is sort of technology, and then finally on the end is sort of all things that are sort of given back to nature. So the black things, the black items don't have a there's nothing associated with them in the key, but they're just categories of different biofuels. So let's just start with woody plant material. What's unique to woody plant material is it's got a lot of lignin in it. And I think we looked at the molecular structure of lignin. It's a big, I don't want to say nasty, but just a very complicated molecule that's one of the structural components of woods in addition to cellulose. And it tends to be tricky chemically in terms of pulling out energy in a clean way. Cellulosic plant material, no lignin. That's the key. It's just this long chain polymer. Starts out as glucose, goes into starch. It's just a bunch of glucoses over and over again. So not as difficult to deal with. Starch and sugary, those are smaller chain hydrocarbons. Oils, so that's fundamentally different. If you think in your mind in terms of calories that we eat, you've got proteins, fats, and starches or sugars. So the oils are fundamentally different in a chemical format than the sugars, if you will. Microorganisms. Now, these things, I mean, you could sort of think of that as perhaps being algae, but you could also think of them as the little bugs that live in your compost and sort of break down these other materials. Obviously, humans are in the mix. We eat oily plant material. We can eat starches. You'll notice that cellulosic plant material does not go into humans. I mean, you can certainly eat cellulose, but we do not have an enzyme in our bodies to produce, to convert it into energy. So therefore, the cellulosic plant material heads off into the livestock. Humans and livestock both make wastes. We can then sort of follow that along into anaerobic digestion, and again, there's a whole class of microorganisms, and I guess I'm a little surprised why those aren't heading off here, but there are microorganisms in the anaerobic digesters that will then make methane. So just sort of following that along, here goes your methane, and then obviously the two things that can come off of a gaseous fuel like methane are heat and engines. So we sort of followed one little thing through the system. What would be another one? Let's go back up to the top here. Woody plant material, size reduction, pelleting. There's your wood stoves. Patrick Brown came in. He talked a little bit about some of his processes. Obviously, that woody material has to get broken down before it can then get pelletized. And there you go. There's your solid fuel. And we had an example of that last week with Patrick Brown's solid fuel. And again, there goes your heat. You could also, if you were burning it in the same way that he is doing in Wisconsin, you could make that into electricity. Another one is pyrolysis or liquefaction. So heating something to the point where the molecules themselves sort of break down, rather than direct combustion. So if you're doing that, then gases come off, all liquids come off, and again, the end result is some type of energetic process, either heat or electricity. Now, this guy, the three keys here to pay most attention to: physical processes. You might think of these as just mechanical processes. So breaking something apart, squishing it together, pulling it out, just moving it around. Nothing's really getting hot, nothing's getting broken down, as is the case with the chemical and thermal. So here, something's getting hot, something's getting hot. Again, hot to the point that the gases are coming off. In the case of conversion, this is going to be more of a biochemical. So you see the microorganisms are extracting from any residues that come off, and then the conversion here is going to be a liquid fuel. And a good example would be your algae, where the oils come out and then become a substitute for petroleum products. Again, you sort of have algae, and again, in every single case, heat and some kind of either electricity or a mechanical system converts it to energy. So that's kind of the big picture on where biomass will end up in this little big energy system. All right. Next, I think this is just a shot of Coppicing, and there's an example of sort of a sustainable bioenergy conversion. Do we have another? Is there another? I wonder if I have another copy of this guy. Do you have it with you?
Yeah.
Oh, okay. Okay. Sorry. I mean, if you want, it's not a big deal. Yeah, fine. Okay. So Coppicing, and I think I've even seen examples of this. If you take a look, down on the Clark Fork, they'll go and sort of trim those willows off, and you'll notice that the willow trees, they're just kind of down to the stump, but the trees themselves are still alive. You'll see these similar sort of woody, stemmy plants, growing up. You're probably familiar with what a willow tree looks like. It's sort of it's a sustainable harvesting of these biomasses, and the plant stays alive. It's not clear cutting, and it sort of serves the dual purpose here in acting as a windbreak or a fence row or a property line. So you're sort of getting dual purposes out of a purpose-grown biomass. And in the book, they talk about short rotation forestry and also short rotation coppicing. And what they mention here, referring to the centuries-old practice of coppicing hazel, willow, like we just mentioned, or other fast-growing trees. And they said, attractive features of the countryside. And then, cut close to the ground, 1 to 4 years, they regrow, etc. And the stump is still there.
Can't they pull those stumps out and chip them up and turn them back into compost?
Yeah, you could, but the point here really is to have sort of a renewable energy. So if the stump comes out, then there's no sort of nucleus of life there to keep growing the. So yeah, I mean, if you were going to convert the land to sort of some conventional agriculture, then yeah, you take the stump out and turn it back into dirt.
Well, can't you turn it back into dirt and put new plants in its place?
Oh, for sure. Yeah, absolutely.
So you don't keep dissipating the nutrients out of the dirt.
Absolutely. Yeah, no, I think that's a critical component. In fact, I'm seeing this practice catching on more and more in Missoula. There's a German practice of, and the name used to be on the tip of my tongue, but just more or less burying waste wood a few feet underground. That becomes a nice moisture buffer. So it's sort of a slower decomposition underground, and the wood is now a nice buffer for moisture rather than the water sort of seeping down through the soils. And as that wood decomposes, yeah, it's just turning straight back into dirt and keeping that carbon in the ground rather than setting it on fire, if you will. So
right.
yeah,
just ripping it out.
Yeah, yeah. Okay, so there's a few other little examples here. Next shot in the book, these are some possible plants for production of cellulosic biomaterials. So, and these are going to be sort of regionally dependent. So you've got sort of a plains, maybe a portion of a continent that's capable of growing trees, or grasslands. So the first one is just bracken there. It looks like a fern type plant. The next one is miscanthus, sort of a big grass, similar to maize. In C, you see this gunera, a large, fast-growing, leafy plant. And again, these aren't woody things. They're just kind of like big grasses and ferns and whatnot. Kelp is another one, obviously growing underwater. And then water hyacinths, things that grow relatively quickly and are sustainable. Okay. Another thing that's mentioned here in the book, it says when used as animal feed, these crops are often called silage, by storing them in silos. In airtight conditions, silages can be used as high-energy feedstocks for anaerobic digestion, along with animal manures. And the Hull's Dairy in the Bitterroot is a good example of that, where they're using animal waste. I don't think they're really actively putting any greens in there, but just animal waste, taking that biogas, burning it, and turning it into electricity. So another example of biomass to energy. Here's a shot of miscanthus again, kind of a tall. In this shot, it looks a little bit more like wheat than corn, but just a sort of a strawish material, straw-looking material. Okay, so some other purpose-grown crops. So here's starches or sugars. These could then be used, if we sort of go back, the starches or sugars back to our categories of energy conversion, anaerobic digestion, and there you would make ethanol or methane. Ethanol in the case of fermentation. Okay, maize harvesting. And here's another tricky one for you in terms of sustainability. So almost certainly that machine is being driven by a petroleum product. And I think, moving into the future, if we're to, actually do this in a sustainable manner, I mean, you would have like a solar-powered robot sort of, creeping across the land, the landscape, or a machine that's just using the same fuels that are being produced locally. So, and then finally, the sugar beets too, and almost certainly this thing is being driven by some petroleum-based machine. We're having a similar issue right now. We're trying to get one of these, earth tub digesters here to process the compost and the food waste from our cafeteria and the one at Sentinel. And so the question is, we need some kind of energy source to drive the mixing equipment, because a lot of times if this stuff stratifies too much, you end up with an anaerobic component and an aerobic component. Really, you want to just stick with one or the other and not sort of mix the two. So if you can keep enough air in there so the microorganisms can have to breathe, you're going to have a colony that's staying aerobic, the waste being CO2 versus anaerobic. So the challenge we're having is, how do you just sort of keep this all using renewable energy and not sort of relying on ancient petroleum sources. And while we're on this topic, I want to take, have I already assigned Shramsky to you? Okay, we'll do a little Shramsky discussion too briefly, because there's a very pesky problem that I want to figure out. We'll just do it here in my office. Okay, so let's just keep cruising through the chapter, and then I'll do the Shramsky. Okay, so here's algae. This is a obviously a purpose-grown biofuel, and so you can think of an algal system as actually being carbon negative, right? So sunlight and air are what comes in. I mean, that's basically about it. There will also be some micronutrients coming into this thing, but basically this whole thing is just sucking CO2 out of the air. Pretty amazing. And just last night I was watching a video when I was Googling the talk that I gave in Billings last week. I saw a really cool shot of just CO2 molecules like going into plants and coming out of submarine operators' noses and all this. But you look at it like, oh gosh, this is actually sucking CO2 out of the atmosphere, and there are a lot of successful companies doing exactly that. And I think I mentioned previously the Algae Aquatech, their green power engine, as truly being a carbon negative energy production facility, and it's actually pretty impressive. Okay, so there's that. This is the straw-fired station, and kind of weird. I mean, you'd kind of think that straw would be better used to feed your livestock rather than being converted to energy, but if you just got a heck of a lot of extra straw laying around, then there you go. Not my idea of efficiency, but I guess I just want to say to each his own. Okay. Now, I think that wraps up the first little section. Let's see how we're doing on time. Fine, let's just keep going for another 10 minutes here or so. Chapter 4, Part 1. Chapter 4, Part 2. All right. This is municipal solid waste, something, and you can see from the state of my office, that I've been avoiding for the last 5 years. I'll make the confession. And really, when it comes down to it, I mean, look at this. So recyclable paper, glass recyclable, metal recyclable, textiles. Take them to Goodwill. I even take my used sponges there, for gosh sakes. I mean, they're made from a material. Any fibers or materials that aren't getting, worn again as clothing go back into this international fiber market, if you will. I mean, the majority of China's paper floats across the ocean right out of California. I mean, it happens. Same thing, the polyesters, the nylons, the you name it, whatever, the cotton. I mean, all of that is going to be either insulation, some kind of building material, or again, clothing. I'm still baffled by the fact that clothing goes into the landfill. It's just bizarro to me. Plastic again, either a building material or, as we saw last week with Patrick Brown's pellets, waste to energy. Organics, put it back in the give it back to Mother Nature. Turn it into food, for gosh sakes. Now this other, I'm not exactly sure what other is in this case. It could be, you're talking your heavy metals. That needs to go back to a materials recovery facility, because you notice that heavy metals are not mentioned here specifically. They don't mention mixed waste. So I am really puzzled by what others are. And in fact, I'm still baffled by the whole notion, even dealing with my friend and colleague, Martin No Runner, who we've been working on a zero waste curbside solution for Missoula for several years now, really with very little traction because it's tough. It's not easy. He still refers to something, and I heard this for the first time 2 days ago, this thing he refers to as trash. So maybe I want to know what trash is, because when it comes right down to it, all this stuff is some form of matter, and okay, it's waste, and you can call it trash, but you're going to find it somewhere on the periodic table, and I'll guarantee you someone's going to find a use for every single element on that periodic table. So, okay, off my little high horse soapbox for a while. All right, this guy, I have not seen a shot of this in in the book, but you can see how, and there are a lot of companies. Florida's got one of these. I think I want to call it Covandia or Covindia in Michigan. So they're working on, okay, so you've got this sort of single stream, conventional municipal solid waste delivery. It's hanging out, it's getting picked up. It's, here's your heat, just like you'd see in a coal-fired power plant. It gets hot, it goes to make steam, make electricity. There's slag, and this could be the other, but again, it's something on the periodic table. Some of it might be heavy metals, but again, send that back to a refinery. Get the iron out of it, get the aluminum out of it, get the plutonium out of it. If someone's building a plutonium reactor in their backyard, but this guy, flue gas, drying and cleaning. There's going to be a catalytic converter here, and then the chimneys in general. This is going to be some CO2, but with the proper back end that feed this CO2 into your algae. I mean, it's just going to become this sort of infinite loop, or to some type of fungal phytoremediation solution. It's where the future is going to be. Okay, so Southeast London combined heat and power. 1994, 420,000 tons of municipal solid waste per year, 31 megawatt turbo generator. And so, again, a lot of this just kind of pick your poison. Do you want to have electricity, or stick the thing in the landfill and deal with all the stinking methane forever? And we can see that the Missoula has sort of that methane stack. I'm sure you've seen it when you drive by the landfill. There's a big methane stack that's just kind of burning 24/7. The idea that CO2 in the atmosphere is perhaps better than methane in the atmosphere, because that's what's coming off of the landfill because of all the organic material. That said, there are 7 states in the United States that are going to ban restaurants and food retailers from putting any organic material in the landfill. It's it's gonna be illegal next year in 7 states in the U.S. So kind of eliminating that methane problem in the landfills. Share of incineration of municipal solid waste. And you can sort of see that Denmark's kind of, leading the pack here. The UK, there's, some incineration going on in France, but they just kind of forgot to get the energy recovery from it.
Is it you saying that Denmark imports trash?
Sweden imports solid waste. They're so efficient with their recycling that they don't have enough solid waste anymore, so they import it from their power plants. Yeah. Okay, so here's some pellets. We saw those, and in fact I've got a jar of them right here on the wall, the conventional pellets that are water soluble and not pretty well separated at this point. So yeah, moving along to another operation. So this is taking oils out of seeds. So running these through a machine that more or less squishes the oil out. It's just an advanced oil press. Okay. The next one, and there aren't too many pictures here, so I'm just going to read through this: pyrolysis and gasification. So just bear with me. I'm going to do a little bit of reading, assuming we're doing okay on time. Yeah, I'll read for another 3 minutes here. So, pyrolysis is this, and I'm on the bottom of page 148. Pyrolysis is the simplest and almost certainly the oldest method of processing one fuel in order to produce a better fuel, in the form of charcoal. So, driving off a lot of the waters, either volatile gases, you're really left with more just kind of a pure carbon. And then that pure carbon can then be burned. In some cases, in the pyrolysis, you'll end up with CO. So carbon monoxide is actually an example of incomplete combustion, and so that'll be a product of pyrolysis also. Not as high an energy content, obviously, of solid carbon, but still some energy to fully combust and make heat from and combine with oxygen. Other more controlled forms of pyrolysis and similar techniques of gasification have since been developed to produce solid, gaseous, and liquid biofuels. So, depending on the exact nature of whatever's going in, the temperatures, the pressures, etc., and you can kind of think of it, I don't know if you've ever driven by a big oil refinery, and that's more or less what's going on. They're sort of cooking those sludgy, nasty oils, more or less. The light volatile molecules go up, the heavier ones come down, and you're sort of left with a set of molecules, if you will, at each stage that have specific energy. Think of your butanes, your propanes, your methanes all coming off because they have different molecular weights and different density. And that's more or less what's going on in those big stacks. And then the tars are at the bottom, depending on their molecular structure. So it's just a way of distilling, taking longer molecules, distilling them, and becoming pure materials that burn really in more predictable ways. Okay, so I'm going to keep going here. Charcoal is traditionally produced in the forest where the wood is cut. The kiln, consisting of stacked wood and covered with an earthware, is allowed to smolder for a few days in a near absence of air, typically at 300 to 500 C. This is slow pyrolysis, so it's sort of allowing the heat to penetrate deep into the wood. If you burn it quickly, everything sort of like peels off on the outside like an onion. But if you do it slowly, little pores and whatnot allow the gases to escape and just sort of the charcoal to remain. I think we saw Haiti and the Dominican Republic. I think we looked at that a little bit, and the deforestation. So, sort of an indictment of overproduction of charcoal, because I think Haiti was relying on that for their economy for quite some time, but they have had troubles with sustainability. The next one, let's look at torrefication. It's the next little section, is the industrial scale thermochemical, so you've sort of got heat and you've got some chemistry going on, treatment of biomass in the even lower temperatures, so 200 to 340 C. It says in this mild pyrolysis process, the biomass, typically hemicellulose, only partly decomposes, giving off some of the combustible volatiles, your COs, your methanes, and perhaps some sulfur compounds as well. The resulting solid torrefied biomass, sometimes referred to as biocoal, because it's going to have a higher carbon content, has approximately 30% higher heat energy content, increased density, and reduced content of undesirable elements such as chlorine in comparison to the original biomass. That chlorine is going to take off while it's being heated. Torrefied biomass is also hydrophobic, just like Patrick Brown's little deal. The plastics in his pellets are hydrophobic. That's why it's still floating there and there's no water penetrating it. Does not absorb moisture from the air. Particularly suitable for co-firing with coal, because it's being stored for an open for a long amount of time. And then there's a whole deal here on pyrolysis. I do want to spend a little more time, so I'm going to take a quick break. 3:40, 4:30. Yeah, we'll take a quick break here at 30 minutes. Get back to it.